Alright, so my presentation is called Fire in the Sky, Humanity's Climb to Space. This is where I take brief excerpts from, this is basically my book report on space history, when I didn't read the entire book. I read the first chapter and I read the last chapter. And so I try to fill in the gaps myself, and it doesn't work that well. But you'll see that. I don't want to ruin the ending. I'll explain some like very minimal stuff. It probably, considering that I'm a first year physics student, doesn't even apply to the real world anymore because they don't tell me what actually happens. So some science behind the journey to the stars, the scientists that helped build the ladder. Of course, I'll be looking at the ladder in a retarded fashion, which is to say back in time, and then leaps forward and back. It's very broken up. And humanity gazing down upon its accomplishments, both in a scientific sense and a physical sense. Here we start with Sir Isaac Newton's universal gravity equation, which was the force of gravity is equal to the universal gravity constant, mass of an object, mass of a bigger object, over the radius between the two squared. That was great. That was he published that in his big book that I forget now because I haven't had a lot of sleep. Principia, I believe it was called. And this essentially sets our goal as the Waterloo Astronaut Training Corps, because without a force of gravity, getting to space isn't really that hard. This is the boundary we had to cross, or we still have to cross, I guess. We as humanity had to cross. It makes it an accomplishment, and it makes it a goal in the first place. But unfortunately, Sir Isaac Newton, back in the 1600s, late 1600s, could not calculate what the universal gravity constant was. As I said there, what the F is G. I thought that was funny. But so he struggled for his entirely long-lived life. He lived well beyond what he really should have back then as far as medicine went. And he couldn't figure it out. And that really stopped his progression into space science right there. He went in to do a whole lot of other things. He argued that light was a particle, and everyone was like, "You're crazy," but then they came back and said, "Oh, I'm sorry, it was a particle." Kind of, but that's what we're talking about today. So, in comes Henry Cavendish. Now, here's a scientist who, he had other professions. Most scientists back then did. They were scientists by hobbies only, and they funded their science through their other jobs. So the richer you were, usually the more science experiments you could afford to do. So Cavendish did some trade work. It wasn't, I didn't really look it up. I was going to say it's not really known, but then someone would be a douche and call me on it. So he managed to use brand new, exciting 1700s technology to determine G. What he did was he took two lead balls, and they were on a series of pillars and levers and stuff, and he would set them beside each other. He knew their mass, and he would measure the microscopic distance that the gravity between the two covered over days and weeks. And he did this over and over and over and over again, as science makes you do. And he finally came out that G was 6.673. I think this is a more scientific exact number that he didn't quite get, but he came really close to it. I mean, for measuring how close two lead balls come together over years and years. So he measured that, and with that, he could determine the mass of the Earth. Now, what was peculiar about Cavendish was, as a scientist, he didn't publish this. He wasn't the one who published this. He died before this was published. He sort of just wrote it in his book, that he did all the experiments in his basement, wrote it in his book, therefore, mass of the Earth is basically 6 times 10 to the 24 kilograms, but he wouldn't have measured it in kilograms because that didn't exist yet. Even in pounds. And he put it on a shelf, probably went to bed. It wasn't discovered till he died and people were flipping through his findings. They said, hey, this guy discovered the mass of the Earth. With this, he sort of defined the barrier. So Isaac Newton said, here's the barrier that we need to get into space, though they probably weren't too concerned with getting into space at the time. And Cavendish said, this is the number. If you want to launch someone into space, use this number, that's how much energy it's going to take. So now the students the world over could calculate how much energy it would take to launch themselves into space. So you have to wonder, why weren't they doing that? Well, let's take me for example. With me and absolutely no rocket ship, it would take 7 times 3 to the 7.355 times 10 to the 10 joules to place me as high as the moon, which is, you know, a little. I got my eyes set high, but you know what? It's the moon. It's not that far, but that's a lot of energy. This is the year 1799, 1800. The Earth's population isn't even 1 billion yet. A young Frenchman is causing some trouble in Europe at this time. He's got some armies, he's got some cannons, cavalry, muskets. This is the technology they are using, and they can. Hey Dan. Cutting in. This is the technology they're using, and they can go, hey, this is how much energy we need to get into space. So humanity sort of had to wait for the technology to catch up. In essence, they needed a little more horsepower to get into space than a horse could provide. Which is where this comes in. That's more like it. That's the Saturn V rocket. It can produce 190 million horsepower. Eat your heart out, Ferrari. The size of that thing, too. That's a beautiful rocket. It can generate 34 meganewtons of force. If you could punch someone in the face with 34 meganewtons of force, they wouldn't exist anymore. The country they're standing on probably wouldn't exist anymore, depending on how small the country is. If you hit Haiti with 34 meganewtons of force, that's the earthquakes. This was Wernher von Braun's masterpiece. I called it the Sistine Chapel of Rockets. 1, because it was so great, and 2, because he didn't really want to build it. They made him build it. He was sort of a slave to the United States. We'll get into that later. But wait, we just jumped 150 years into the future here. We went from horse-drawn carriages to this bitchin' rocket ship with no real explanation of how people thought of rockets. So